Okay, so in the second part of the lecture on quantum error correction with germanium host qubits, I will discuss simple setups for quantum. So in the previous part, I was talking about classical error correction, where I was specifically discussing transmission of a single classical bit. And now I'd like to convert this scenario into a quantum scenario. So first, I'd like to introduce a specific quantum channel. So as a classical channel was defining how transmission of a single classical bit works, now we want to describe how a quantum channel works. And to describe quantum information, typically we use the density matrix for that. So if I want to describe a state of a qubit, then the density matrix of this qubit is a 2x2 matrix shown here. And this matrix is Hermitian and positive semi-definite. And if I imagine that I send in this quantum bit to a channel for transmission, then this noisy quantum channel is described by map, which is telling me if I put in qubit state rho, then what is the outcoming qubit state n rho. And in this part of the lecture, I will focus on a simple channel, a simple example for a channel, which is called the bit flip channel. Or more precisely, a quantum bit flip channel with bit probability p, and it is shown by this equation. So it's going to map density matrix rho to an outcome output density matrix n rho by this rule. So n rho will be equal to 1 minus p rho plus p x rho x, which means that with 1 minus p probability, this channel will just preserve the incoming qubit state, and with p probability, it will perform a bit flip, an X operation on this qubit density matrix. So this is a very simple model of bit flip errors. And then this mapping is, of course, regular in the sense that it preserves density matrix properties, so it will map a density matrix to another. Now, my goal here is to extend the classical error correction scheme shown in part 1 to a quantum version. And a naive idea in that direction would be to try to use redundancy again. And as we did in the classical case, use redundancy in terms of cloning or copying the original state which you want to transmit. So this would mean that we could start from such a state when the first, such a two qubit state where the first qubit is a superposition, the second one is one of the computational basis states, and just use the second one to make a copy of the first one. So here in this product state, the two states are the same. Now the problem is that in quantum mechanics, there is a no cloning theorem which is forbidding this kind of copying. So this naive extension of the redundancy idea to the quantum case does not work at all. So we have to use a different idea, which is also based on redundant encoding. And this idea is the following, that instead of cloning, we will use an entangled encoding. So if I want to encode a single qubit state alpha 0 plus beta 1, as shown here, then I will encode it in such an entangled state which reads alpha 0, 0 plus beta 1, 1, which is entangled 2 qubit state. And actually, to make this 2 qubit states, it's relatively easily because we just need only a single canonical 2 qubit gate, the CNOT gate. So here you see the CNOT gate. So this very simple circuit consisting of a single CNOT will do the job. So if we input this alpha 0 plus beta 1 superposition and this 0 computational basis state, then on the output we will actually find exactly this. Now, starting from this point, the next important and useful concept is the parity of such a state. So actually the parity is a concept which is defined for computational basis states of a 2 qubit system. For 0, 0, the parity is even or 0. For 1, 1, the parity is also 0 or even. And if the 2 bit values are different, so for example 0, 1 and 1, 0, then the corresponding parity is odd or 1. And the parity has this interesting appearance in this scenario that if you look into this encoding state alpha 0, 0 plus beta 1, 1, this is actually has a well-defined parity, even though it's a superposition of two different computational basis states, 0, 0, and 1, 1. Both of these computational basis states have an even parity or a zero parity. So this state is a parity eigenstate in that sense. Another useful concept brought in by this parity definition is that actually if there is a bit flip happening, so if I have this state, but now on this encoded state I have a bit flip happening, then actually I can detect this single bit flip by measuring the parity, because the effect of the single bit flip on this state will be that it becomes alpha 1, 0 plus beta 0, 1, or the other way around. So actually 0, 0, and 1, 1 will be converted to computational basis states which have the opposite parity, odd parity. So by measuring the parity of such a 2-qubit state, actually we can learn that the bit flip happened. This is a very important ingredient in error detection in the quantum scenario. And this error detection is actually leading to a way to have a better transmission through the channel. I did a simple numerical example here. So if no bit flip error occurs, so if the input state alpha 0, 0 plus beta 1, 1 just goes through the channel, it has a probability of 1 minus p squared. For the example, I take 10% errors. P is now 0.1. If I evaluate this, that's 0.81, so 81% probability for this case, no bit flip error occurs. Then, if I can measure the parity afterwards, I will find an even parity, or parity value will be 0. If a single bit flip occurs, this can be easily calculated that it happens with a probability of 2p times 1 minus p, which is in this numerical example when p is 0.1 is just 0.18. Then I will measure an odd parity, or a parity value 1. And if 2-bit flip occurs, and this has a probability of 1%, then I will again measure the parity as even or 0. So now if I use this error detection trick to actually select out, to post-select for the even parity cases, then I will find that if I consider only even parity cases, then the error I can calculate by taking the actual errors with even parity, which had a probability of 1% when 2-bit flip happens, and this has to be divided by the probability of an outcoming state which is even, which has even parity, which is 82%. So in this case, the error probability I get after this post-selection scheme is slightly above 1%. And this is a huge decrease compared to the p equals 10% original error probability, which is characterizing a single qubit. So this entangled encoding up here is indeed useful in the sense, in this sense, if we can actually measure the parity. So the final question here is that how to measure the parity of this. I will show you this simple circuit. So you need a few more ingredients to measure the parity. One ingredient is an extra qubit. So D1 and D2 up there, these are the qubits which have been used so far. This is what these are called typically data qubits in this context. And then in order to measure the parity, I also introduce a third qubit, which I call M1, and I will call this the measure qubit. What you need is 2 more gates. So if you want to measure the parity of D1 and D2, the joint parity of D1 and D2, then you can do it with this simple circuit, which consists of actually 2 CNOT gates. CNOT gates are useful, they appear again, and also a measurement on the measure. So let me just quickly prove step by step that indeed this circuit measures the parity of the combined parity of D1 and D2. So if both of these qubits are 0, that means, since these are control not operators conditional on the D1 and D2 qubits, so if these are 0, then nothing happens to the measure qubit, so we will measure it at 0. So if the data qubits are in the state 0, 0, then it will lead to a measure qubit measurement outcome. If, on the other hand, the second data qubit has a value 1, that means that this second CNOT will actually flip the measure qubit, and thereby we will measure it at 1. So if we see if this is an example when the parity of these 2 data qubits is odd, and this will indeed lead to a measurement outcome of 1. when we measure the. Another example, when the data qubits are in the state 1, 0, in this case, actually it is the first CNOT which is active, so that's going to flip the measure qubit value. The second CNOT is passive, it doesn't change this, so the measurement will be again 1. And finally, in the last configuration, when both of these data qubits are in the 1 state, then both of these CNOTs will be activated. So there's going to be a flip here and a flip there, and the net effect is that the measurement will yield 0. So if we look into this truth table down here, we find that indeed this circuit does what I promised. So it will actually read out the joint parity of the two. In conclusion, two CNOTs and the measure qubit in this circuit yields parity. Now, this parity measurement can be used either in a basic quantum error detection circuit for quantum error detection, or in a basic quantum error correction circuit. Now, on this slide, I'm showing the quantum error detection circuit, where I actually summarize what I told before. So I have these two data qubits and I have this measure qubit. The procedure starts by having this data qubit number 1 prepared in some superposition. Then the next step is to spread this information or encode the qubit into the joint state of these two qubits. Then these qubits are sent through these noisy channels when a bit flip can happen. After that, there is a parity measurement or parity check or error detection region here, which is just copied from the previous slide with these two CNOTs and the measurement. And then if this measurement finds out that the joint parity was 1, then we simply discard this measurement, we discard this run, because we know that then a bit flip happened in one of the channels. Otherwise, if this is 0, that's a sign that with a high probability there was no error happening in the channels, and in that case we can close this circuit with a measurement of the data. And a generalization of this is a basic quantum error correction circuit, when we don't only detect the error but also correct it. And this is a somewhat more complicated. It has more quantum bits. So in particular, it is using 5 quantum bits, 3 data qubits, and 2 measure qubits. The starting point is very similar. So we start with a prepared superposition on the data qubit. The next step is similar to the previous slide when we have a spreading or encoding step, when we encode this single qubit of information into an untangled state of these 3 qubits, the 3 data qubits. Then these 3 data qubits are sent through the noisy channels. After that, we do, again, parity measurement or parity check or error detection step here, which consists of a number of CNOTs and also exploits the 2 measure qubits and also does measurements on them. And in this scheme, the 2 measurements will bring us 2 classical bit values, which can be either 0, 0, 0, 1, 1, 0, and 1, 1. And what these 2 bit values are informative on what kind of error happened in this channel. So which of the 3 bits was flipped in the noisy channel. So based on this information, which is often called the syndrome in error correction schemes, we can make a decision how to correct the error. Which qubit should we flip back? Is it the first one, second one, or the third one? Or maybe do nothing? So what is the active error correction step we should make to correct that errors with which? This is done here. So active error correction means that one of these operations, nothing, x1, x2, or x3 is applied. And then the scheme is finished with a measurement of. So this is a basic quantum error correction circuit, which is called a quantum repetition code, or the quantum bit flip code, because it protects against the bit flip error. So this concludes the second part. So here my goal was to introduce the simplest quantum error correction circuit, the repetition code, which protects against a special type of errors. And in the next video, I will go on and discuss recent progress and also future challenges of quantum error correction with germanium holes and qubits.